Polished script. Ever wondered how quantum computers could revolutionize machine learning? Today, we're diving into the science behind training quantum models and why some methods work better than others. Let's break it down step by step. Imagine teaching a machine to recognize not just cats versus dogs, but specific breeds, like distinguishing a golden retriever from a poodle. That's multi-class classification, a big deal in AI. But when you throw quantum computing into the mix, things get tricky. The quantum computer spits out data in a weird, abstract format, like a secret code. To make sense of it, researchers use a classical neural network as a translator. Think of it like a bridge. The quantum part does the heavy lifting, and the classical layer turns its messy output into something we can understand. Now, how do you teach this bridge to get the right answers? That's where training comes in. The team used a tool called Atom Optimizer, a smart algorithm that tweaks the model's settings, like adjusting a recipe until the cake tastes perfect. They set the learning rate, how big each adjustment is, to 0.001 and ran it for thousands of rounds, 1,000 for one task, 5,000 for another. But here's the twist. When they limited the number of quantum measurements, called finite shots, they switched to a different technique called the parameter shift rule with mini-batch training. Why does that matter? Think of it like taking photos in low light. If you use a high-speed camera, you might get blurry shots. But if you switch to a slower, more precise mode, you can still get clear images, just with different trade-offs. In quantum computing, finite shots mean the machine can't measure every detail perfectly. The parameter shift rule helps it adapt, like using a flashlight to spot patterns in the dark. Here's the kicker. Even with these limitations, the model still learned effectively. By combining quantum processing with classical refinement, it balanced speed and accuracy. It's like having a superpowered calculator that also knows when to double-check its work. So what does this mean for the future? These training techniques show that quantum machine learning isn't just about raw power. It's about smart, adaptable methods. By blending quantum and classical tools, researchers are making progress toward real-world applications, from drug discovery to climate modeling. Thanks for watching. If you're curious about how quantum models learn, hit subscribe. And let me know in the comments, what kind of quantum AI would you love to see next? Stay curious. Ever wonder how machines learn to recognize things, like how your phone knows that blurry photo is actually a cat? Well, researchers are experimenting with completely new ways to teach AI, and one of the coolest ideas involves mixing quantum physics with machine learning. Let's break it down. Here's the classic approach. Imagine teaching a kid to recognize dogs. Traditionally, you'd show them hundreds of dog pictures first, then later hand them a list of labels like dog, cat, and bird. That's the two-step method, separate data and labels. But what if you combine them? Like showing a picture of a dog and the word dog at the same time, then testing them with other words. That's one-step learning. It's like teaching a kid by saying, this is a cat, but this isn't, all in one go. Now here's where it gets wild. Scientists tested this idea using a quantum computer, specifically an ion trap system. Think of it like tiny charged atoms, or ions, floating in space, acting as quantum bits or qubits. These ions can exist in multiple states at once, thanks to superposition, and influence each other instantly, thanks to entanglement. The team used this to train a quantum system to generate handwritten digits, like the famous MNIST dataset, but with a quantum twist. The results? Let's talk numbers. In perfect conditions, the old two-step method was just slightly better. But when they added noise, like static on a radio, the one-step approach shined. Especially for task A, where the quantum system outperformed classical methods. For task B, though, the two-step still held strong. Why? Because some tasks still benefit from that traditional separation of data and labels. But here's the kicker, this isn't just about digits. It's a glimpse into how quantum computing could revolutionize AI. By leveraging quantum states, researchers aren't just mimicking classical methods, they're exploring entirely new ways to process information. Imagine training models in seconds instead of hours, or solving problems that are impossible for today's computers. So next time you see a handwritten number, remember, behind the scenes, quantum computers might be learning to write them too. The future isn't just digital, it's quantum. Thanks for watching and stay curious.